morning, everyone. Welcome to this summer school advanced course in risk assessments and which are the basic concepts of toxicology and risk assessment. Let's go to toxicology. So just to warm you up a bit, toxicology, what do you think about? When you hear toxicology, which processes, which pathways do you remember? Yeah, exactly. Toxicodynamics, toxicokinetics. These are processes that are important, the absorption, the distribution, metabolism, and excretion. So that's important to keep in mind. Also, when we're going to do risk assessment, you will see you have to think about these concepts. Then organs. I think you all know that there's many organs that we can study. What is the effect on the liver, on the heart, on the brain? Like, it depends on your research question, of course, and also if you want to see which health effects come out, you're going to study specific organ systems. Then the public health impact, there you will see that in the past, also a bit now, but in the past, the focus was mainly on chemicals. A lot of chemicals, metals, pesticides. We still do that, but that was the main focus. Then the endocrine disruptors came, so a lot of this risk assessment was focusing on these kind of compounds, including genetic toxicity tests, epidemiology data to actually do risk assessment. But now, in as we call the 21st century toxicology, new approaches are coming, but also new hazards. There's new emerging hazards and nano materials we know have been working on, but also nanoplastics are coming into play, or microplastics. But also other things like electric waste. Apart from the chemical waste, there's more going on. And instead of only looking at the organ systems, there's also that we're going to look more molecular with omics techniques, but also here you see mitochondrial toxicity. So apart from systems toxicity, we also are going to look molecular, like how is it going on in the different molecular levels. I'll come back to all of that later, but just to give you some context for the talk. So this is just here to say to you, okay, why is risk assessment important? Maybe you've heard a lot in the news, at least in Belgium and the Netherlands. There's a lot in the news about PFAS. PFAS is an endocrine disruptor. And why is it all of a sudden becoming an issue? Although there is already a directive in place that PFAS production should be reduced or even stopped. But still, there is risk assessment about it ongoing. The reason being is because they stay into the environment for a long time. So how does PFAS come into the environment? For instance, firefighters that were doing exercises or when there was a fire, the foam of the firefighters contains PFAS, and that then stayed in the environment, leached to the water systems, and then it comes back to us through the groundwater, the drinking water. So that is one risk. The other one is, of course, from the industries that were producing it. It could leak through the soils, the water, and the same thing. But since the half-life of PFAS is long, it stays in the environment even after it was produced. So now there's still risk assessment and risk management ongoing for these chemicals. So just to show you that at any stage, at the production phase, but also after the production phase of certain chemicals, risk assessment is important. So what is risk assessment? I think you all know research. In research, we look at effects, we expose ourselves or we expose an in vivo model, and then we see what is the effect according to your hypothesis. Risk assessment, of course, uses these data, but they're going to look at, is there a risk? Because there might be a hazard. I'll come back to that. There might be hazards, but is there a risk? And there's different steps, and I will go over all of these steps during my talk. And then after risk assessment, there's the risk management. There will be some talks later that will deal with risk management and examples. And of course, there's also risk communication. Okay, when you know that there is a risk, how are you going to communicate that to your audience, to your public, to the community? How will you do that? And in the end, you will also see there is a talk on that and how you can deal with that and what you have to keep in mind when talking to community. Okay, so step by step. If we plan a risk assessment, you generally have to ask all these questions. And the how, what, why, where, when. Why? Because we want to know what is the risk, where is the risk, or what is the hazard, where is the hazard, and when does it occur? Also, how do the people get exposed? Who gets exposed? There might be modifying factors. Is it only an elderly population? Is it also children that gets exposed? Because age can be a modifying factor, for instance. Critical windows, a bit related to age, but here it's more like, is it a prenatal exposure? Do we get a critical window? The development phase is, it's very vulnerable for exposures and interventions, both from the food, but also chemical exposures. So critical windows are important to keep in mind as well. Health effects for sure, but then we ask us like, okay, which are the health effects? When do they occur? Is it a long-term effect? Is it an acute effect? Which systems are affected? Is it just a certain system, maybe only the liver? Is it a total body reaction to the exposure? And time is more about acute and chronic and things like that. How long? Is it just one time? Acute exposure, does that already have a risk? Or are there occupational exposures which happen chronically every day, but at low doses maybe, but still they might have an effect even at low doses if there is a chronic exposure. Okay, so these are the 4 steps that I showed you before, and we're going to go over them one by one, starting with hazard identification. So as I said, I've been talking about risk and hazard, but what is the risk? What is the hazard? Maybe it helps when I show this picture. Who is at risk here? And what is the hazard? Yeah, exactly. And the sun is the hazard. So the hazard is that people can be exposed to the sun. But who is at risk? Yeah, the one that are not on the umbrella. So these people here, you can see from the picture, they are at risk. The hazard is the sun, they are at risk because they don't protect themselves. The other ones under the umbrella, they protect themselves. So they take away the exposure. So they take away the exposure, so they take away the risk. The risk is a lot lower because they are protecting themselves. So what you have to remember is that the risk is the combination of hazard and exposure, because the ones under the umbrella are not exposed, they have less risk. There might still maybe be some UV light coming through the umbrella, but the risk is lower because the exposure is lower. So this is a bit more in words. What is a hazard? What is a risk? So just make sure that you don't mix them up. And the hazard is any chemical or physical agent or exposure that there's out there that can cause harm. The risk is then, of course, depending on the exposure, the dose, the occurrence, and how long is your exposure to it. So frequency needs to be taken into account as well. What I said, acute and chronic. So dose and frequency have to be taken into account. If you talk about hazard, which hazards do you have in mind? What kind of hazards should we do risk assessment on? Chemicals, for sure, chemicals, but which are other hazards currently that can pose a risk on our health? And the plastics, I said already, indeed. Food toxicants, for sure. So there's a whole array, actually, like I say, that can be out there. There's also going to be a case on radiation, air pollution, water pollution, pharmaceuticals, even from the drugs, and drugs can be contaminants. So there's a lot of compounds and chemicals out there that can pose a risk to our health. So they are hazards if we get exposed to them. The health effects that we then study, you will think, okay, it's a disease, but it can also be your total health, what we express in DALI. So the disease in general. So this is the life years that you have left without disease. So if you get exposed and there's a health risk, then your DALY will decrease because the years without being diseased or lower. And of course, yeah, the other ones, like cancer, reproductive effects, it can have effects on cardiovascular factors, allergies, but even mortality. Yeah, so it can also lead to mortality. So these are all the health effects you have to study and see in a risk assessment. Okay, then sources of data. As I said, I'm giving the overview here. More presentations after me will go into more depth on all of these topics. But just to give you an overview of the types of data that you come across in a risk assessment. So first of all, you can have chemical analysis with models, what we call structure-activity relationships. So it's a computer model that has been built over the years, and that compares compounds that were toxic in the past, and now they're comparing based on their chemical structure, on their chemical characteristics. They're going to say, okay, this is a harmful chemical or this is not. So that's the first step. So they call it in silico analysis. The next one is in vitro studies. So you can have cell models, 2D, 3D, a lot of 3D models are coming into place, where you expose and you can see, okay, what are those response relationships, for instance. Then we're moving to the in vivo. Where is my pointer gone? Oh, here. We're moving to the in vivo part. So it can be small animals, like the zebrafish, are used a lot for development and reproductive toxicology. But you can also work with rodents and other animal models to look more into the physiology and the in vivo part. Both chronic and acute toxicity are tested in these in vivo models. And then, of course, there is the humans. As you know, it's not as easy to do control tests with humans, but there are clinical studies, there are epidemiological studies where data can be used from to do risk assessment. So there will be a talk afterwards from Stefano Bonassi, who will say what is the value of epidemiology in risk assessment. Okay, so toxicological studies. To sum up, what do they do? It's the word itself. You study the toxicity of a compound, poison, and their interactions with the body. Then you can have non-human experiments, you can have human experiments, and based on that, you're going to set exposure limits. The problem is only that sometimes in vitro models, you go to high exposure doses, while in humans, it's actually more often low exposure levels. So there's mathematical models that have to be used to do extrapolations and so forth. And for EPA, for instance, the European agency, you see that they use a margin of safety or a reference dose to set limits. What is the advantage from toxicological studies? As I already said, they can be controlled. You work with an in vitro system, you work with an in vivo system, they can be controlled. There's no contaminants in the study, other exposures that might show interaction. So, of course, you want to know in the end what is the effect of the mixture, but if you're studying first what is the effect and what are the underlying mechanisms, it's good to have a controlled system because that facilitates how to interpret the results. On the other hand, of course, there's a lot of uncertainties. Like I said, usually we use a lot of higher doses in vitro and in vivo models, which are not always relevant for humans because they are exposed to lower doses, but more chronically. And indeed, again, the extrapolation, because a mouse, okay, they have similar physiology, but a mouse is not a human, so you have to do extrapolations. Then epidemiological studies, as I said, Stefano will talk about it, but you all know, I think, what epidemiology studies do. They take a cohort or a longitudinal study, and they look at the incidence or the prevalence of certain diseases, certain health effects, and do associations with exposures. Like, are there exposure health associations that we can observe in a population? They are, of course, based on the human exposure, so that seems more relevant. And they want to find not only risk factors, of course, they want to know what is the risk here, what are the risk factors, but they also want to know, okay, what are preventive factors? How can we make sure that a disease is prevented? So they look at both sides. So the advantage is, of course, that you're working with humans directly. You have, in a big population, you can see a lot of incidents of diseases. So you have a lot of data, because with animal studies, we usually have groups of 5 animals per condition or something as small. Well, in a human, you have a big group. You provide actual data of the disease incidence, and while in mice, it is simulated. And the dose responses are not needed, because you just measure what they are exposed to. You don't have to mimic those responses. On the other side, of course, as you know, they're less controlled. So there's a lot of other exposures ongoing that you don't know, does it affect the association or the exposure that I'm studying? So you work a lot with confounders, they call it, but again, that will be explained later, like factors that can influence your association. So the question then is, like, what is the cause? What is the effect here? So is there a direct causal relationship? And of course, there's often occupational exposures. So that also needs to be taken into account. Like, are people exposed at work? Are people exposed at home? Are people exposed on their way to work? So there's a lot more factors to take into account, because people move around. We're not sitting in a cage or a petri dish. Okay, so far so good. So another type of data is where you check in the toxicological process. So we already mentioned toxicokinetics, toxicodynamics. So all these data are also taken into account, but it depends how you take them into account. So first, you're going to, of course, look at uptake, distribution in the body, metabolism, and excretion. And these are taken into account. Maybe it's not the parent component that is toxic, but maybe one of the metabolites is toxic. So then it's important to take toxicokinetics into account. The toxicodynamics is then, of course, more looking into, okay, how is it then transported in the cell? Where does it end up? Does it end up in the mitochondria? Does it end up in the fat deposits? Where does it end up? So how do the cells react to it? How does the organ react to it? So you're more going to look at organ systems. Of course, that's closer to the health effect, but you also have to take into account the toxicokinetics in order to know, okay, how can we prevent the exposure, or where, and the dose, how can we estimate the dose? But I'll again come back to that. Okay, so that's a bit about hazard identifications and the type of data there are. You will see examples later that use these data in certain cases and situations. The second step is dose response assessments. So let's first talk about dose. I think you all know about Paracelsus by now, that he said, okay, everything is poison. It just depends on the dose. Water, for instance, is water toxic? Can water be a poison? I see some people nodding. I see some people saying no. Well, it depends on the dose. If you drink 5 liters or maybe 10 liters of water in one day, you can actually have kidney failure and like die. So it can be toxic. But of course, if you drink just normal levels, it's not toxic. So it all depends on the dose. And here again, what is the dose? The dose is usually expressed in milligrams per kilogram of body weight per day. And so that's important for pharmaceuticals, but also for other exposures, they look at it like that. And what is the dose? Okay, so talking about doses, it is important to remember that when you read a dose in a paper, it depends what dose do they report. It can be, for instance, the potential dose. So what is the dose around you in the environment that you are potentially exposed to? That's one thing. The other thing is the applied dose. What dose did you get on your skin? What dose did you get into your lungs? Did you inhale? That's also important. That's a different type of dose. Then the internal dose is after the uptake. Like, okay, how much is the dose in our body, in our blood. And then the delivered dose is, again, how much does it go to the organ systems? And what do we measure in the liver, for instance? And then you have the biological effective dose, because there can be a certain concentration in your liver, for instance, but does it have a health effect? So what is the biological effective dose? That's also another way of looking at dose. Then, how do we do dose response assessments? Of course, you look at the relationship between the dose and the toxic effect. You all might know, maybe from an in vitro experiment, you have different concentrations, you have a nice concentration curve, you see what is the effect. So it's as simple as that. It also describes the likelihood of the adverse effect. Like in the beginning, maybe you don't see anything, so maybe at low doses there's no effect, and then all of a sudden you get an effect which is observed. That's what I said. So maybe at low doses, you don't see anything. It's from a certain threshold, you observe something. The shape of the curve, you can have linear curves, you can have S-shaped curves. I will give you some examples for that. And that has usually to do with if a compound is genotoxic or non-genotoxic. Is it carcinogenic or not? Because, yeah, I'll come back to it, but carcinogens are believed to usually always have an effect when you are exposed to it. Just to put it into molecular perspective, so I think you all know if you're exposed to a chemical or another stressor here, and it is a genotoxicant, it will react with the DNA. So your DNA get damaged, and this usually leads to either apoptosis or non-controlled cell proliferation, and then in this example, it's cancer, but it can also be inflammation, and that you get chronic diseases in another way. But usually, genotoxic compounds end up in cancerous outcomes. But then there's a whole other layer that are not directly genotoxic. Your compound can have an effect on DNA methylation, on your epigenetics. The epigenetics then again have an effect on your gene expression. Your gene expression can affect DNA repair, or it can affect other mechanisms in here that help prevent the chemical from causing the adverse health effect. So there's another layer down here, also genetic variations, of course, play a role. Chemicals, yeah, if they cause genetic variation, it's usually a mutation, so then it is genotoxic. But if you think about all of these processes, these are non-genotoxic processes that can still cause cancer or another chronic disease. So they can influence hormones, and there's a hormone imbalance. They can influence oxidative stress. You get inflammation. So all of these can actually play a role in a non-genotoxic way. Why is it important? I'll show you some examples. But first to say, there's two steps in your dose response assessments. One is, of course, to look at the dose response relationship and see, okay, when do we see effects at which dose? But the other one is maybe even more important, is how do we extrapolate it to the humans? How do we translate it? What is, a dose that we find that has an effect in animals? Does it also have an effect in humans? So that's important to take into account. Then determining the thresholds, as I said, some chemicals work with a threshold and other chemicals do not have a threshold. I'll show you some examples about that. Again, remember that I'm just putting the scene here, so I'm not going to details, but to show you that there's two types of dose response. One is the one with the threshold. So here you see at the low doses, there's no effect, and all of a sudden we see effects occurring. So that's why we call this point a no observed adverse effect level, because before that point, there were no effects observed. And then at a certain point, you see a lot of health effects coming on. So at that point, you say, okay, this is the lowest dose that we see an adverse effect occurring. And then, of course, what I said, if we want to translate to humans, we have to actually put uncertainty factors. So maybe at this dose, we don't see an effect in the animal, but in order to translate it, the dose is put lower. So the exposure limit is put at a lower level. Here are some examples. So if you go from mice and you want to translate it to humans, because there's different kinetics and different dynamics in a mouse, you put an uncertainty factor, usually an uncertainty factor of 10. And if you then talk about human, which are all different in sensitivity, for instance, children, she comes in and it's cracking. If you think about translating it to children, then it's another 10 times factor that they usually do. Maybe this example will help you. So imagine you were studying metal mercury, and these are the exposure levels that you have for monkeys, for rats, different doses. And then they use these data to extrapolate. So they start from the monkey data because they're more relevant for the humans, but they only have a low observed effect level. And what we want is a level at which there's no observed effect. So the factor of 10 is applied for a no adverse effect animal, no adverse effect level in animals. So to translate this to humans, we apply another factor of 10. So a 10-fold lower limit. And to translate this, for instance, to a children's population, another factor of 10. So if you then translate this to levels for an adult of 70 kilograms or a child of 15 kilograms, then these would be the allowed exposure levels per day. So this is how we come to these limits. And it's usually called the reference dose, but sometimes you will see that they talk about acceptable daily intakes or minimal risk levels. They all refer to similar thing. Another concept I just want to mention, but there will be a whole talk about it on Wednesday, is benchmark dose. Benchmark dose is a new approach. So not the standard dose activity relationships, but in the benchmark dose, they actually start from a predefined effect. At what dose do we see this predefined effect? And they're applying a confidence interval, so more like a dose range that you're going to look at. There are some advantages and disadvantages about it. They also assume that there's no threshold. The advantage compared to what I just explained, the reference dose, is that it has more data, more basis to calculate actually the reference dose. Also, compared to the no AL and the low AL, the benchmark dose approach takes into account the magnitude of the study. So bigger studies will have a bigger impact than smaller studies. Data from smaller studies will have less of an impact. And then your no AL might be different from your benchmark dose based on the magnitude of your studies. You have information on the shape of your curve in these benchmark dose modelings and about the risk and the exposure near the benchmark dose, because we work with a confidence interval. It's not just one dose, there's this confidence interval. But you can imagine such modeling is more laborious than the standard no AL, low AL approach. Some data are just difficult to model, and mixtures and then other data are not, but you will see that in an example on Tuesday. And yeah, you're working with a model, so it depends on which kind of model you choose, what your outcome is. So that's something to keep in mind as well, that you set your criteria properly. And yeah, it's more conservative than non-observed effect level approaches. Again, just setting the scene, more will come later. But then we've been talking about thresholds, but certain chemicals are carcinogenic. And then we assume, at least in the traditional approach, we assume that there is no threshold. Because if you think about, I'm just going to talk about the one-hit model, like one exposure or one mutation can already lead to cancer. And this is the worst case scenario that they keep in mind when talking about carcinogens. So in this case, they say there is no threshold because one hit can cause an effect. And that's why they won't look at a curve like we did before, but they will look at the linear part. They say, okay, there is no threshold. So in cancer studies, they look at the cancer slope factor. They see, okay, what is the rate at which we see an effect? And the cancer slope factor is, like I said, again, expressed in milligrams per kilogram per day, like the doses. But what it means in cancer is, for instance, here, it means 2.4 cases of cancer are observed per 100,000 people. So when you see values of cancer slope factors, that's what they mean. And here you can see that the first one is actually the most cancerous. Okay, that was a bit of a teaser on those responses. Now we're moving into the exposure assessment. So dose response exposure assessment, you can see that they link a bit to one another, but still we try to put them in steps. Because in exposure assessment, it's more about, okay, what is the magnitude of exposure? What is the route of exposure? Inhalation, swallowing, dermal contact. The duration, is it what I said before, acute, or is it an occupational exposure at low levels chronically? Frequency, again, like bit linked to acute and chronic, but more like, yeah, how many times a day, or is it just during 1 week and then for another week not anymore? So all of these things have to be taken into account. Another other two terminologies, not to confuse, is, I think the most known one is the exposure route. I think that's clear for everyone. I just said inhalation, dermal contact. These are the exposure routes. How does it get into our body? But what is often forgotten is the exposure pathway. How does it come from where it is produced, where it is created? How does it get to us? Because between that, the source and us, there can a lot of things can go on. For instance, here you can see maybe in the environment, the compound can already be transformed from the original compound to a metabolite or a derivative from it. And then the way we are exposed to it is different from the source. So these are things to keep in mind as well. The way we measure exposure can be done in two ways. We can have a direct exposure measurement, or we can have an indirect exposure measurement. The direct exposure measurement after COVID, maybe you all know that there were a lot of sensors put in place to measure the air quality. But also, for instance, black carbon, you will see that at Vito on Tuesday or tomorrow, that you can carry a device with you where there's a filter and they actually measure the black carbon exposure on your body, let's say. So you take the machine with you and then it's a more realistic direct measurement of the exposure. We can, of course, go a step further and go look in the body, like in blood, hair, urine, really measure, okay, how much of that chemical or that compound has actually entered the body? What do we measure as an internal dose? So that is, of course, also a direct measurement of exposure, and this is done a lot in biomonitoring studies. Then the way to indirectly measure is a bit different. Their models come into place again. And what you see here is measuring stations. So in the top here, for air quality, for instance, we use a lot of measuring stations that detect the level of the air pollution. And based on these measurements, there's models created that can map actually how the air pollution is in your area, in your living area, close to certain streets. So they model based on wind, of course, and based on how close you are from to a busy road and so forth. They can model a scenario of the exposure. Are you going to work by bike, for instance? So for the way you communicate or commute, I mean, they can make a scenario. But you can also, again, go into the body, but maybe you don't have access to blood, or the compound was so quickly metabolized that it is hard to pick it up in the blood. Then think again about these different types of doses that I explained. So here you can see, you can of course measure the internal dose, but maybe you will have to look at biological effective dose. So maybe measuring oxidative DNA damage can be a marker for your exposure, or certain types of oxidized lipids and so forth in your urine can be a marker of exposure. So you might have to look for a biomarker that gives you an indirect measurement of your exposure. But again, later, Roger will talk about biomarkers and explain this in more detail. The final step of the risk assessment is then where you actually combine everything, the risk characterization. So it's making the puzzle of all the data you've gathered. You have data on hazard identification and characterization, you have data on your dose response models, and you have data on your exposure assessment. So puzzling all of that together will help you do risk characterization. To keep in mind is then, okay, I said puzzling all together is, for instance, is a compound now carcinogenic? And then you're going to look at these classifications, like, is it a likely carcinogen, or is it a really, really strong carcinogen, or not so likely? Another aspect to take in mind in risk assessments is the weight of evidence. This is now applied a lot in mode of action and adverse outcome pathways. Again, a talk that will follow later. But what I want to show you is here on the side that you see sometimes they say, okay, there's a strong evidence for this link, or there's moderate evidence, or there's actually only weak evidence. So in order to know which are the health effects or which are maybe the intermediate health outcomes, you need to have enough evidence to actually prove that there is a risk, that there is an adverse effect. Another important thing also to take into account is sensitive populations. We already mentioned it a little bit. And the prenatal life is an important critical window where babies, unborn babies, can be exposed to chemicals already. But also, later in life, the aging population might also be more vulnerable to a certain exposure. So that's something to keep in mind. Occupational exposure, we also talked about that. This is maybe a sensitive population for pesticides or other chemical exposures. And then there is the disease, or let's say people with maybe a lower immune system. They might be more vulnerable to certain hazards and certain exposures. One of the final concepts for risk characterization that I want to mention is the mode of action. I already said it a bit. As you know, I talked about the traditional CHANTOX and the toxicity testing in the 21st century. In the traditional toxicity testing, a lot of genetic toxicology was in play, a lot of standard assays that are performed to actually look at those responses, look at what are the limits. But in the new approach, the 21st century approach, we're looking into molecular levels. We're not looking only at the standard tox test, but a lot of the omics come into play. And then again, modeling and computational systems are becoming more and more important. And maybe you've heard about toxicogenomics. So there they look at gene expression and how this can lead to genotoxic effects and to adverse health outcomes. So that's a new layer of data and concepts that come into play. And also should be taken into account in risk assessment, because you want to see, okay, how does a compound come from A to B and what is the mode of action? Okay, that were the 4 steps about risk assessment. Just to round up my talk, I briefly want to say something about risk management, just one slide, to say that there can be different things to do. Of course, you can do risk avoidance. You can advise the public to avoid it. You just ban the production of the chemical, but it's not always as easy to do that. I'll jump then here to safety standards, or I mean, in the middle, of course, you can say, okay, there's a 0 tolerance. It's again, like you still want to avoid the exposure, but sometimes you just need these compounds, and it might just be as simple as avoiding exposure. That's what the picture in the beginning, the sun, we cannot take away the sun. The sun is there. So the hazard will stay. but it's just how we protect ourselves and which measurements we put in place that will reduce the risk. So that's what is with the safety standards. They can say, okay, for instance, occupational exposure, there's certain safety measurements, certain clothing, certain maybe masks that need to be worn in order to take away the risk, to take away the exposure. So that's to keep in mind. It's not always as simple to say, okay, we ban it, we reduce the exposure by taking the chemical from the market, but sometimes it's as easy just to work with safety measurements. So this was the overview that we started with. And then in the end of this training, there will also be a talk about risk communication. I'm not going to go into detail there, but just remember that this is as important. How do you bring the message now to the public, to the community, what to do with this risk, how to deal with it, how to live with it. So what do I want you to remember from this opening talk? That risk assessment is a way to interpret toxicological information and process it in how we're going to put it into decisions, into public health measurements, and so forth. That there's two types of risk assessment, the ones dealing with the thresholds, which are usually the non-genotoxic chemicals that can then still have an adverse outcome, and the ones that follow a linear curve, a non-threshold dose-response relationship, which are usually the genotoxic chemicals and primarily lead to cancer. Just remember that there are different ways to assess this, that there is a no-AL approach and there is a benchmark dose approach, where we will come back to in more detail later. And that for the genetic cancer risk assessments, we work with these cancer slope factors because they assume the one-hit model. And just to maybe finish with a warning, you will see sometimes we have to use models because that's the best what we have. We try to impute as much data as we have. But whenever you run a model, always use your common sense. Always think, okay, what I modeled and the outcome, does it make sense? What is the biological mechanism behind it? So don't just fill in the model and don't just say, okay, this is what comes out. Try to interpret it and try to make sense of it. Because remember, the risk communication, in the end, you will have to translate this to the public and you will have to say, what are the implications?